For number one, if you look at the graph here, notice that we have these vertical beams going like this. So we're going from this x value to this x value. So we're going to go from -2 to 2. And notice the orientation of the graph. Here it's like a top versus the bottom. So we want to go the top equation minus the bottom equation. Now this actually has a typo because right there you see where it says y equals x squared. That's supposed to represent the graph of the parabola, which is here. But honestly, the graph, the equation for that parabola should actually be y equals x squared plus 1. So that is a typo in the question. So it should actually be top minus bottom with dx because we're using x's, otherwise it'd be dy if we were using y's. So let's go top minus bottom, where the top equation is the parabola, which should be x squared plus 1, because the y-intercept is 1, minus the bottom graph, which is this linear function, and that equation is correct, x minus 2. And if you simplify the integrand here, that should become like x squared minus x plus 3, and everything else stays the same. So that settles number one. And just FYI, let me draw for you a quick example of something that's not top minus bottom, because that one was top minus bottom. But if you had a graph that looked something like this, let's say you had something that looked like this. That's not a function, but let's just ignore that for now. Let's say you had something like this. That would be an instance of right minus left. And for something like that, it'd be right minus left, where it'd be this equation here would go there, and then the left equation here would go there. But for number one, for sure, it was top minus bottom, with a little typo there for number one. Now for number two, let's see. If you look at the graph there, and if it's blurry on the video, you can just pull it up on your phone, of course. But that to me, again, looks like a top minus bottom. And the cutoffs are gonna be this x coordinate to that x coordinate. So the cutoffs would be like right there. And the left x coordinate would be -2, so that's the lower limit. And then the other one would be 1. So you want to use the points of intersection of the two graphs. And then you want to use the upper equation minus the bottom equation. So top minus bottom, protected in parentheses, dx. Oh, and by the way, going back to this one here real fast, for that one, you know how I said it'd be right minus left? That would have been dy at the back, and these would have been y's instead of x's, and these would have been pulled off of the y-axis, or these would have been y values instead. So going back to number two, we have top minus bottom, so it's dx with x coordinates. The top equation looks like it's the linear function, x plus 3, minus the bottom one looks like the parabola, which is x squared plus 2x plus 1. So if they clean that up, I'll let you do that, but that is the setup for number two. So for number three, they want us to give them an expression for the outer radius. So we're pretending that this dotted line is going to be the axis of revolution, so that this red region is going to revolve around this axis of revolution, where here what you do is I always grab like a really sharp or a bold pen, and I go from the axis of revolution to the closest graph. That's the inner radius. And then go to the same axis of revolution and then go out to the outer function. And again, you can draw it there, or it doesn't really matter where you draw. This is just random. But the point is, you go from the axis to the close, and then from the axis to the far. The axis to the close one, that's the inner radius. And then your axis to the outer, or to the one that's far away, that's the outer radius. And when I say axis, I'm not talking necessarily about the x and y axis, although I could. When I say axis of revolution, I'm talking about the dotted line that they pretty much always draw for you, and they denote with one of these little arrows, like one of these loops. Okay, so this is our axis of revolution. Axis to close is the inner, axis to far away, that's the outer. So the question is, what is the length of this purple? Well, here's what I want you to see. Notice that if I were to go to the axis of revolution, I can go to the outer. I could have drawn this different ways, right? The point is I'm going from the axis to the outer function. So notice that we can describe any one of these purple pillars arbitrarily, because if you notice here, we stop here. We stop at these points. And really, these points, since we're going vertically, we're actually talking about the y coordinates, right? We're talking about this y coordinate, this y coordinate, this y coordinate. We're talking about a height. So we're talking about the y coordinates. But the problem is that really all of these y coordinates have this little gap missing, because you see there is a little vertical gap between the x-axis and the axis of revolution. So this little vertical gap needs to be deducted from the y coordinate. Now for this upside down parabola, the equation of that upside down parabola is this, that there. And you can think of this equation as that being the actual y coordinate, because the x coordinate is whatever. The y coordinate is what you get when you plug the x into the x. So that is the whole y coordinate. But from this, we must deduct that little baby gap, which is, if you look at the graph, it has a height of 1. So what we're gonna do is we're gonna take this y coordinate, and from it, we're gonna deduct 1. We're going to deduct 1, take 1 away from it, and that, if you wanna clean it up, it would of course be this, right? But that, which is this, that is the arbitrary height of these purple pillars, which is the outer radius of this model. So let's take a look here at number 5, I think that is. So why don't we put the 2 in the front, and then notice that this is actually gonna be a natural log. So we're gonna have natural log of x minus 1 with the 2 in the front. But the thing is, anytime you when you go natural log, you wanna use absolute values to ensure that you don't natural log a negative quantity. So again, remember that the derivative of natural log is 1 over this, which is why the antiderivative of that is, natural log of that. And the 2 just goes along for the ride. Now this has to be evaluated from -2 to -1. So if you plug in -1 right there, it's gonna be -2 in parentheses, but then you hit it with absolute values and it becomes +2. So it's 2 ln2 minus, now you plug this into that, it'd be -3, but the red absolute value turns it into +3. And so I think this is what they had in the multiple choice. By the way, this could actually be cleaned up to many things. One of the things that could become is something like this. So this could become that if you use log properties, but they didn't do all that. I think that's where they left it for that one. Now for number 6 here, we have, if you look at this, this is actually gonna be a U substitution. And you can recognize that this is a U substitution because if you look at this inner function, the 2x squared plus 3, the derivative of that is 4x, which is in the numerator. So this is actually a U substitution. So we're gonna let U equal 2x squared plus 3, and we're gonna let U equal 4x dx. So if we rewrite this, and temporarily I'll just ignore these limits. For now, let's write everything in terms of U. So here's a negative, here's that. Now 4x dx, that gets replaced by du. And this is the 1 there. Now the bottom, in parentheses, is U, right? Because that's there, but it's gonna be U squared. See that? That's what I have there. Everything here replaces everything there. All right, the du replace these 2 pieces. There's gotta be something up top, so just put a 1. Let me kick the negative out to the front. It's not that big a deal. And if you want, I'll also bring in the U squared upstairs to make it negative. Now ignore that for now. How do I take the antiderivative of this? Well, you add 1 and divide by that new power. Remember that? That's like the power rule, but backwards. You add 1 to the exponent, divide by that new exponent, and then you can keep that negative in the front if you want. That's -1 times this. And let's clean this up. So this is -1 times U to the -1 over -1. These negatives knock out. So really it's just U to the -1 equals. And U to the -1 is just 1 over U. But instead of U, let's write down what we had originally. So this is 1 over 2x squared plus 3. And now you can use the original limits of integration from 0 to 3. And if you plug in 3 there, it'll be 1 over, what is that? 1 over 21 minus, if you plug in 0, it's 1/3. So whatever that is, I'll let you figure that out. That's the answer to number 6. And let's times it by 7. -6 over 21 divided by 3, -2 7. That should be it. So look at the answers. That should be it for that one.